So for example, sometimes you want to calculate the observed power as a function of frequency. So let's say you have a scatter, and you shine a plane wave from bottom. And then if you draw the pointing vector line, then you'll find something like this, as we have seen many times in the class before. To calculate the power observed by the scatter, you basically draw a virtual box surrounding this scatter. Let's say this box is omega. Then this observed power as a function of omega is simply the line integral, surface integral of the net power flux density going into the box. So if there's no obstruction here, then all the flux lines going in will go out, so the power absorption will be 0. But if there is some absorption, for example, if all the power is absorbed by the scatter, then you will have a positive net power flux going into the box. So this is a way to calculate observed power inside the scatter. But one thing to note is that this frequency domain pointing vector is not the Fourier transform of the time domain pointing vector. So the reason is that actually the reason why this is not the case is that there's a theorem called Parseval's theorem, right? So according to the Parseval's theorem, if you define the frequency domain pointing vector as the Fourier transform of the time domain pointing vector, then Hartwell theorem tells this. Right? But this is not the relation we want to have. What we want to have is something like this. So the left-hand side means that all the power integrated over time, which means the total energy transferred through some cross-section. And the right-hand side is the all the power integrated over the all frequency components. So they should be the same. So we want some relation like this, not this. So that is one way to see why the frequency domain pointing vector is not simply the Fourier transform of the time domain pointing vector. So the correct way to calculate the frequency domain pointing vector is to Fourier transform ET and HT separately. To get the frequency domain E field and H field, and then calculate S omega S E omega cross H omega conjugate. So if you carry out that Fourier transform, this is the Fourier transform, and for discretized fields, you get right, so basically this is DFT. Discrete Fourier transform, and here, if the time is discretized, then frequency is also discretized. So your frequency points are this. Here, one thing to note is that the capital N is the total number of time steps. So it's proportional to simulation time. And as this N increases, your frequency space, frequency sampling becomes finite. Right? So if you want to, for example, calculate the observation spectrum with very fine resolution, you have to run long simulation. Okay. There's a problem in calculating actually the pointing vector. The problem is that E and H fields are not collocated. What I mean by that is you have this E script. example, if you want to calculate the g component of the pointing vector, you have to calculate this quantity. But this EX and HY, they are defined at different locations. So you want to multiply this EX and HY, but they are defined at different locations, EX here and HY here. The second term is the same. You want to multiply EY and HX, but they are located at different locations. So to evaluate this quantity, you need to interpolate one of the fields. So more specifically, what you need to do is to calculate SG at the bottom surface. Basically, you need to interpolate EX at the center of the bottom surface. So say this is ijk point, then this is I plus f j k, and you have another EX here, which is EX I plus f j plus 1 k. So EX at the center of the bottom surface is right, and multiply this with HY. You want to interpolate HY at the center of the bottom surface. Then there are 4 HY, which is defined here, here, and center of the back surface, and the bottom back surface. So you have this HY, and also this HY. So basically, you want to calculate HY's. So I'll just write down the expression. So that is HY. The first one is this one is space is too limited, but that first one is I plus half j, k plus half, the bottom one, this one, is hy I plus half j k minus half. And the third one is hy I plus half j plus 1 k plus half. And the fourth one is hy I plus half j plus 1 k minus half. So you have to average these four quantities to calculate the hy at the center of the bottom surface. And then you have to again add the product of the two interpolated quantities, which is ey and hx. Okay. Are there any questions?
That should be a minus, right? Minus ey times hx.
Oh, yeah. Thanks a lot. So, the absorption cross-section, for example, is calculated as So you can calculate this denominator from the plane wave you use to eliminate the scatter, and you can calculate this surface integral pointing vector using pointing method calculated by the previous steps, and do the surface integral. And let's say this absorption cross section is range from omega minimum and from the omega minimum to omega maximum is the, let's say that is the range you are interested in. Then your incident plane wave should contain these components, frequency components. So the incident plane wave is usually Gaussian in time. So the center frequency and the frequency range, you choose something like then this Gaussian pulse as this Gaussian pulse has center frequency at omega 0 and has a width and delta omega. And if you transform this, then JT is something like